When we move into stoichiometry, we are taking everything we know about moles, molar mass, Avogadro's number, and gas volume at STP, and applying it to balanced chemical equations. Stoichiometry is all about using those balanced equations as a roadmap to connect different compounds together. Just like with mole conversions, we are going to build unit maps. But now, we will also use the coefficients from balanced equations as conversion factors to switch between identities. These coefficients are called mole-to-mole ratios. If two compounds are in the same balanced equation, we can convert between them. But in order to do that, we have to be in moles before we can switch to a new identity. For example, in the formation of water, I could convert from H₂ to O₂, from H₂ to H₂O, or from O₂ to H₂O. According to the balanced equation, I would need 2 moles of H₂ for every 1 mole of O₂, or 1 mole of O₂ for every 2 moles of H₂O, or 2 moles of H₂ for every 2 moles of H₂O. These mole-to-mole ratios are basically like a recipe to create new compounds. We put in the ingredients on the reactant side and get out the finished recipe on the product side. It is also important to know the language of stoichiometry. Reactants are consumed in a chemical equation and products are formed. If you are ever converting to a reactant, you are calculating the amount that was required in order to create the products. If you are converting to a product, you are calculating the amount that should be produced without any errors, also known as the theoretical yield. Just because you have a value for a reactant in a problem does not mean you end up with that much at the end in real life. It represents what was used up in the reaction. The amount of product you calculate is what was made. A helpful way to picture this is to think of a machine line system in a factory. Reactants are the inputs that go in, and products are the outputs that come out after the process is complete. Every stoichiometry problem will have a unit map that will start with a value, unit, and compound, and it will end with a unit and compound that we are solving for. The compound at the end will usually not match the one we started with. This is where we must use a mole-to-mole ratio from the balanced equation to convert to the new identity. This means we always need to be in moles in order to make the conversion. The middle ground will still be moles, because moles allow us to connect different compounds fairly using the coefficients in the balanced equation. If we try to skip moles, we will end up with mismatched units or mismatched identities. So moles will always anchor our conversions, and then we can convert to other units for the new compound based on what the problem is asking for. In this video, we are going to go through stoichiometry problems in 4 main categories. First, we will look at mass to mass conversions, where we start with grams of one compound and use the balanced equation to find grams of another compound. Then we will practice mole ratio problems, where we directly apply the coefficients from the balanced equation to connect one substance to another. After that, we will combine mole to mass and mass to mole problems, which allow us to connect amounts of substances across different units. Finally, we will work through complex conversions that bring together grams, moles, liters at STP, and particles all in one unit map. The key is to carefully track your units and compounds step by step, cancel them out correctly, and always make sure the identity matches until you are ready to switch to a new identity using the mole ratios from the balanced equation. By the end of these practice problems, you will see that stoichiometry is really just an extension of mole conversions, with the balanced chemical equation providing the ratios we need to connect everything together. The first category will be mass to mass conversions. This means that we are going to start with grams of one compound, and we need to eventually get to grams of another compound with multiple conversions. The trick here is to convert to moles of the first compound using the molar mass. Then we use the mole-to-mole ratio from the balanced chemical equation to convert to moles of the final compound. Finally, we convert back to grams using the molar mass of the final compound. Mass-to-mass conversions will always have 3 conversion factors in 3 steps: molar mass of the first compound, mole ratio using the balanced chemical equation, and then molar mass of the final compound. If an equation is not given, we have to write it and balance it first. Number 1. Given 5.00 grams of H₂ reacts with excess O₂, how many grams of H₂O are produced? The problem mentions a reaction, so we need to write the balanced chemical equation first. H₂ and O₂ react to create H₂O. To balance, we need a 2 in front of H₂ and a 2 in front of H₂O. For this unit map, we are starting with 5 grams of H₂ and ending with grams of H₂O. The first thing to notice is that we have a new identity at the end. To be able to convert to the new identity, we have to be in moles to use the mole-to-mole ratio. To convert from grams of H₂ to moles of H₂, we'll use the molar mass of H₂. 2 hydrogens will have a molar mass of 2.02 grams of H₂ for every 1 mole of H₂. To convert from moles of H₂ to moles of H₂O, we will use the coefficients in the balanced chemical equation in front of each. There are 2 H₂s and 2 H₂Os, so the mole-to-mole ratio will be 2 moles of H₂ for every 2 moles of H₂O. From moles of H₂O, we have to convert to grams of H₂O. To do this, we will use the molar mass of H₂O. 2 hydrogens and 1 oxygen will give us a molar mass of 18.02 grams of H₂O for every 1 mole of H₂O. Our unit map is now complete, so we can start canceling out units. We start with 5 grams of H₂ over 1. In the next fraction, we put 2.02 grams of H₂ on the bottom and 1 mole of H₂ on the top. In the next fraction, we put 2 moles of H₂ on the bottom and 2 moles of H₂O on the top. In the next fraction, we put 1 mole of H₂O on the bottom and 18.02 grams of H₂O on the top. We make sure all units cancel out. Grams of H₂ cancel out, moles of H₂ cancel out, and moles of H₂O cancel out. We are left with grams of H₂O, which is the unit and compound needed for our final answer. Multiplying and dividing all values, we get 44.6 grams of H₂O. Number 2, how many grams of CO2 form when 10.0 grams of C₂H₆ combust completely? This problem is a combustion reaction because C₂H₆ is a hydrocarbon, and it reacts with O₂ to produce CO2 and H₂O. To balance, we will need 2 C₂H₆, 7 O₂, 4 CO2, and 6 H₂O. For this unit map, we are starting with 10.0 grams of C₂H₆ and ending with grams of CO2. Since we are converting to a new identity, we must first convert to moles of C₂H₆, so we can use the mole-to-mole ratio to convert to the new compound, moles of CO2, and then grams of CO2. To go from grams of C₂H₆ to moles of C₂H₆, we use the molar mass. 2 carbons and 6 hydrogens will give us a molar mass of 30.08 grams of C₂H₆ for every 1 mole of C₂H₆. Next, we need to convert from moles of C₂H₆ to moles of CO2, using the mole-to-mole ratio from the balanced chemical equation. Looking at the balanced chemical equation, the coefficients showed 2 C₂H₆ and 4 CO2. So the mole-to-mole ratio will be 2 moles of C₂H₆ for every 4 moles of CO2. From moles of CO2, we can next convert to grams of CO2 by using the molar mass of CO2. Carbon dioxide has 1 carbon and 2 oxygens, giving a molar mass of 44.01 grams of CO2 for every 1 mole of CO2. We can now set up all units to cancel. We start with the given value, 10.0 grams of C₂H₆ over 1. In the next fraction, we put 30.08 grams of C₂H₆ on the bottom and 1 mole of C₂H₆ on the top. In the next fraction, we put 2 moles of C₂H₆ on the bottom and 4 moles of CO2 on the top. In the next fraction, we put 1 mole of CO2 on the bottom and 44.01 grams of CO2 on the top. Grams of C₂H₆ cancel out, moles of C₂H₆ cancel out, and moles of CO2 cancel out. We are left with grams of CO2. Multiplying and dividing all values, we get 29.3 grams of CO2. How many grams of NaCl form when 12.0 grams of Na reacts with excess Cl2? This problem is a synthesis reaction because sodium reacts with chlorine to produce sodium chloride. When the problem mentions excess chlorine, this means that sodium is the limiting reactant, and we should be using sodium to solve for any other reactant or product amounts. To balance, we'll need a 2 in front of sodium and a 2 in front of sodium chloride. For this unit map, we are starting with 12.0 grams of sodium and ending with grams of sodium chloride. Since we are converting to a new identity, we need to first convert to moles of sodium so we can use the mole-to-mole ratio to convert to moles of sodium chloride and then grams of sodium chloride. To go from grams of sodium to moles of sodium, we use the molar mass. Sodium has a molar mass of 22.99 grams of sodium for every 1 mole of sodium. Next, we need to convert from moles of sodium to moles of sodium chloride using the mole-to-mole ratio from the balanced chemical equation. Looking at the balanced equation, the coefficients are 2 sodium and 2 sodium chloride. So the mole-to-mole ratio is 2 moles of sodium for every 2 moles of sodium chloride. From moles of sodium chloride, we can next convert to grams of sodium chloride using the molar mass. Sodium chloride has 1 sodium and 1 chlorine, giving a molar mass of 58.44 grams of sodium chloride for every 1 mole of sodium chloride. Now we can set up all units to cancel. We start with the given value, 12.0 grams of sodium over 1. In the next fraction, we put 22.99 grams of sodium on the bottom and 1 mole of sodium on the top. In the next fraction, we put 2 moles of sodium on the bottom and 2 moles of sodium chloride on the top. In the next fraction, we put 1 mole of sodium chloride on the bottom and 58.44 grams of sodium chloride on the top. Grams of sodium cancel out, moles of sodium cancel out, and moles of sodium chloride cancel out. We are left with grams of sodium chloride. Multiplying and dividing all values, we get 30.5 grams of sodium chloride. The second category will be mole ratio problems. These are the simplest type of stoichiometry conversions because we stay in moles the entire time. For these problems, we will start with moles of one compound and end with moles of another compound. To make this conversion, we only need the mole-to-mole ratio from the balanced chemical equation. The coefficients in front of each compound tell us exactly how many moles of one substance react or form compared to another substance. Since we are already in moles, we don't need molar mass, or Avogadro's number, or liters at STP. We just need the ratio from the equation. Number 4, in the equation 2 aluminum plus 3 chlorine yields 2 aluminum chloride. How many moles of aluminum chloride are produced from 1.5 moles of aluminum? The equation is already balanced. For this unit map, we are starting with 1.5 moles of aluminum and ending with moles of aluminum chloride. We are staying in moles the whole time, so we only need the mole-to-mole ratio from the coefficients for aluminum and aluminum chloride. The coefficients show 2 moles of aluminum for every 2 moles of aluminum chloride. Setting up all units to cancel, we start with 1.5 moles of aluminum over 1. In the next fraction, we put 2 moles of aluminum on the bottom and 2 moles of aluminum chloride on the top. Moles of aluminum cancel, and we are left with moles of aluminum chloride for the final answer. Multiplying and dividing the values, we get 1.5 moles of aluminum chloride. Number 5. How many moles of water form when 4 moles of H₂ combust with O₂? This problem uses a combustion equation for hydrogen. Even though a combustion equation with hydrogen will look slightly different than a normal combustion equation with a hydrocarbon, if O₂ is reacting, it will be classified as some kind of combustion. H₂ and O₂ react to produce H₂O. To balance, we need 2 H₂ and 2 H₂O. For this unit map, we are starting with 4 moles of H₂ and ending with moles of H₂O. We are staying in moles the whole time, so we only need the mole-to-mole ratio from the coefficients for H₂ and H₂O. There are 2 H₂ and 2 H₂O, so the mole-to-mole ratio is 2 moles of H₂ for every 2 moles of H₂O. Setting up all units to cancel. We start with 4 moles of H₂ over 1. In the next fraction, we put 2 moles of H₂ on the bottom and 2 moles of H₂O on the top. Moles of H₂ cancel, and we are left with moles of H₂O for the final answer. Multiplying and dividing the values, we get 4 moles of H₂O. Number 6. If 6 moles of sodium hydroxide reacts with sulfuric acid, how many moles of water form? This problem is an acid-base neutralization where an acid and a base will react to form water and a salt. We write and balance the equation. 2 sodium hydroxide plus sulfuric acid yields sodium sulfate plus 2 water. For this unit map, we are starting with 6 moles of sodium hydroxide and ending with moles of water. We are staying in moles the whole time, so we only need the mole-to-mole ratio from the coefficients for sodium hydroxide and water. There are 2 sodium hydroxide and 2 water, so the mole-to-mole ratio is 2 moles of sodium hydroxide for every 2 moles of water. Setting up all units to cancel, we start with 6 moles of sodium hydroxide over 1. In the next fraction, we put 2 moles of sodium hydroxide on the bottom and 2 moles of water on the top. Moles of sodium hydroxide cancel, and we are left with moles of water for the final answer. Multiplying and dividing the values, we get 6 moles of water. The third category will be mole to mass or mass to mole conversions. These require 2 conversion factors. If we are starting with moles and ending with grams, we go from moles of the starting substance to grams of the ending substance. We use the mole-to-mole ratio from the balanced chemical equation, and then the molar mass of the final compound. If we are starting with grams and ending with moles, we go from grams of the starting compound to moles using the molar mass, and then we use the mole-to-mole ratio to get to the moles of the final compound. So in these problems, we always have 2 steps and 2 conversion factors, 1 mole ratio and 1 molar mass. Number 7. How many grams of iron 3 oxide form from 3.00 moles of iron and excess oxygen? This problem is a synthesis combination reaction of iron with oxygen producing iron 3 oxide. We write and balance the equation. 4 iron plus 3 oxygen yields 2 iron 3 oxide. For this unit map, we are starting with 3.00 moles of iron and ending with grams of iron 3 oxide. We are ending with a new identity, iron 3 oxide, so we need to use a mole-to-mole ratio to convert to the new compound. We have to be in moles to convert to the new compound, and we already are. So we can go straight from moles of iron to moles of iron 3 oxide using the mole ratio, and then to grams of iron 3 oxide using the molar mass of iron 3 oxide. From the balanced equation, 4 moles of iron make 2 moles of iron 3 oxide, so the mole-to-mole ratio is 4 moles of iron for every 2 moles of iron 3 oxide. The molar mass of iron 3 oxide is 2 irons and 3 oxygens, which is 159.7 grams of iron 3 oxide for every 1 mole of iron 3 oxide. Setting up all units to cancel. We start with the given value, 3.00 moles of iron over 1. In the next fraction, we put 4 moles of iron on the bottom and 2 moles of iron 3 oxide on the top. In the next fraction, we put 1 mole of iron 3 oxide on the bottom and 159.7 grams of iron 3 oxide on the top. Moles of iron cancel, moles of iron 3 oxide cancel, and we are left with grams of iron 3 oxide for the final answer. Multiplying and dividing the values, we get 240 grams of iron 3 oxide. Number 8. How many moles of NH3 are produced from 68.0 grams of N2 reacting with H2? This problem is a synthesis combination reaction of nitrogen with hydrogen producing ammonia, NH3. We need 3 hydrogens and 2 ammonia to balance the equation. For this unit map, we are starting with 68.0 grams of N2 and ending with moles of NH3. We are ending with a new identity, NH3, so we need to use a mole-to-mole ratio to convert to the new compound. We have to be in moles to use the mole-to-mole ratio, so we first need to go from grams of N2 to moles of N2 using the molar mass, and then convert from moles of N2 to moles of NH3 using the mole ratio from the balanced equation. The molar mass of N2 is 2 nitrogens, which is 28.02 grams of N2 for every 1 mole of N2. From the balanced equation, 1 mole of N2 makes 2 moles of NH3. So the mole-to-mole ratio is 1 mole of N2 for every 2 moles of NH3. Setting up all units to cancel. We start with the given value, 68.0 grams of N2 over 1. In the next fraction, we put 28.02 grams of N2 on the bottom and 1 mole of N2 on the top. In the next fraction, we put 1 mole of N2 on the bottom and 2 moles of NH3 on the top. Grams of N2 cancel, moles of N2 cancel, and we are left with moles of NH3 for the final answer. Multiplying and dividing the values, we get 4.85 moles of NH3. Number 9. Given 22.0 grams of carbon dioxide, How many moles of oxygen are required in the reaction? This problem is a synthesis combination reaction of carbon with oxygen producing carbon dioxide. The equation is already balanced. For this unit map, we are starting with 22.0 grams of carbon dioxide and ending with moles of oxygen. We are ending with a new identity, oxygen, so we need to be in moles of carbon dioxide to use a mole-to-mole ratio to convert to the new compound. To do this, we will first go from grams of carbon dioxide to moles of carbon dioxide using the molar mass, and then convert from moles of carbon dioxide to moles of oxygen using the mole ratio from the balanced equation. The molar mass of carbon dioxide is 1 carbon and 2 oxygens, which is 44.01 grams of carbon dioxide for every 1 mole of carbon dioxide. From the balanced equation, 1 mole of oxygen makes 1 mole of carbon dioxide. So the mole-to-mole ratio is 1 mole of oxygen for every 1 mole of carbon dioxide. Setting up all units to cancel, we start with the given value, 22.0 grams of carbon dioxide over 1. In the next fraction, we put 44.01 grams of carbon dioxide on the bottom and 1 mole of carbon dioxide on the top. In the next fraction, we put 1 mole of carbon dioxide on the bottom and 1 mole of oxygen on the top. Grams of carbon dioxide cancel, moles of carbon dioxide cancel, and we are left with moles of oxygen for the final answer. Multiplying and dividing the values, we get 0.500 moles of oxygen. The fourth category will be complex conversions, and these are the longest problems because they can involve 3 or more conversion factors. In these problems, we might have to connect grams, moles, liters at STP, and even molecules or atoms all in one unit map. These problems combine everything we have learned: molar mass, Avogadro's number, 22.4 liters at STP for gases, and the mole-to-mole ratio from the balanced equation. The key here is to always start with the given value over 1, and then carefully set up each conversion so that the units and compounds cancel step by step. If you keep moles as your middle ground and use the mole ratios from the balanced equation, these longer problems will work out the exact same way as the shorter ones. Number 10. How many molecules of H₂O form when 10.0 grams of H₂ combusts? This problem is a combustion reaction of hydrogen. 2H₂ plus O₂ yields 2H₂O. For this unit map, we are starting with 10.0 grams of H₂ and ending with molecules of H₂O. We are ending with a new identity, so we will need to go from grams of H₂ to moles of H₂ using molar mass, use the mole-to-mole ratio from the balanced equation to get moles of H₂O, and then convert to molecules of H₂O using Avogadro's number. The molar mass of H₂ is 2.02 grams of H₂ for every 1 mole of H₂. From the coefficients, 2H₂ makes 2H₂O, so the mole ratio is 2 moles of H₂ for every 2 moles of H₂O. Avogadro's number is 6.022 times 10 to the 23rd molecules for every 1 mole. Setting up all units to cancel, we start with the given value, 10.0 grams of H₂ over 1. In the next fraction, we put 2.02 grams of H₂ on the bottom and 1 mole of H₂ on the top. In the next fraction, we put 2 moles of H₂ on the bottom and 2 moles of H₂O on the top. In the last fraction, we put 1 mole of H₂O on the bottom and 6.022 times 10 to the 23rd molecules of H₂O on the top. Grams of H₂ cancel, moles of H₂ cancel, moles of H₂O cancel, and we are left with molecules of H₂O. Multiplying and dividing the values, we get 2.98 times 10 to the 24th molecules of H₂O. Number 11. What volume of oxygen gas is needed to react with 5.00 grams of methane CH₄ at STP? This problem is a combustion reaction, so CH₄ reacts with oxygen to produce carbon dioxide and water. To balance the equation, we need 2 oxygens and 2 waters. For this unit map, we are starting with 5.00 grams of CH₄ and ending with liters of O₂ at STP. We are ending with a new identity, O₂, so we will need to go from grams of CH₄ to moles of CH₄ using molar mass, use the mole-to-mole ratio from the balanced equation to get moles of O₂, and then convert to liters at STP using 22.4 liters for every 1 mole. The molar mass of CH4 is 16.05 grams of CH4 for every 1 mole of CH4. From the coefficients, 1 CH4 reacts with 2 O2, so the mole ratio is 1 mole of CH4 for every 2 moles of O2. Setting up all units to cancel, we start with the given value, 5.00 grams of CH4 over 1. In the next fraction, we put 16.05 grams of CH4 on the bottom and 1 mole of CH4 on the top. In the next fraction, we put 1 mole of CH4 on the bottom and 2 moles of O2 on the top. In the last fraction, we put 1 mole of O2 on the bottom and 22.4 liters of O2 on the top. Grams of CH4 cancel, moles of CH4 cancel, moles of O2 cancel, and we are left with liters of O2. Multiplying and dividing the values, we get 13.9 liters of O2. Number 12. How many atoms of sulfur are in 64.1 grams of sulfur dioxide produced in a reaction? This problem follows grams to moles to particles. For this unit map, we are starting with 64.1 grams of sulfur dioxide and ending with atoms of sulfur. We are ending with a new identity, sulfur atoms, so we will go from grams of sulfur dioxide to moles of sulfur dioxide using molar mass. Use the mole to mole ratio inside the compound, 1 sulfur atom for every 1 sulfur dioxide, and then go from moles of sulfur to atoms using Avogadro's number. The molar mass of sulfur dioxide is 64.07 grams of sulfur dioxide for every 1 mole of sulfur dioxide. Avogadro's number is 6.022 times 10 to the 23rd atoms for every 1 mole. Setting up all units to cancel, we start with the given value, 64.1 grams of sulfur dioxide over 1. In the next fraction, we put 64.07 grams of sulfur dioxide on the bottom and 1 mole of sulfur dioxide on the top. In the next fraction, we put 1 mole of sulfur dioxide on the bottom and 1 mole of sulfur atoms on the top. In the last fraction, we put 1 mole of sulfur atoms on the bottom and 6.022 times 10 to the 23rd atoms of sulfur on the top. Grams of sulfur dioxide cancel, moles of sulfur dioxide cancel, moles of sulfur atoms cancel, and we are left with atoms of sulfur. Multiplying and dividing the values, we get 6.02 times 10 to the 23rd atoms of sulfur.